here we are in Chapter 4, and we're dealing with Chapter 4, Section 8, and we're talking about friction. So friction in physics, it's a rough subject for a lot of students, and it starts to make everything a little bit more realistic, more real life, and it involves just a new force, and the new force is called the force of friction. So what is the force of friction? Well, the force of friction is a force that opposes motion, or it opposes when we're trying to move something in a certain way. It's a force. So we write it this way. Force, and in the book it says subscript Fr, and that's for friction, and that equals the force of friction. It's a force which will try to oppose motion. It's a vector, so it has a direction. There are two different types of frictional forces. We have the force of friction kinetic, which is equal to we have this, the force of friction kinetic is the type of friction, sliding friction. Okay. And the other type of friction is called the force of friction static. And what that deals with is non-sliding friction. I believe I just might have said friction. It's static is non-sliding friction. So what I'm saying here is there are two types of friction. Okay. So friction is now a new force, and the way you get friction, the book tries to explain it, but I don't think they do a very good job. They don't show you the type of pictures I would have liked them to have shown you. If you looked at a landscape, and if you looked at take an electron microscope and magnify a surface about 1,000,000 times. If you would look at a nice, smooth, plain surface, after you magnify it 1,000,000 times, it's not going to look so nice and so smooth anymore. It's going to look like an alien landscape. It's going to be really rough and really bumpy and full of nooks and crannies. And so when we have friction, what happens is we're trying to slide two objects together. So if we're sliding two objects together, what happens is friction would be something like this. When one surface and the other surface, we're attempting to slide them. And on the microscopic level, since no surface is completely smooth, if you magnified it 1,000,000 times, you would see it's all very, very rough looking. So if you take one surface and another surface, and they're both on the microscopic level relatively rough looking, when you put them together, then those nooks in those crannies are kind of interlocking with each other. And when you try to move something, so for instance, if I'm rubbing my hands this way, so if this would be the bottom surface of my hand on the microscopic level, and this would be the other surface, when I put them together, they interlock. So if I attempted to push them this way, these fingers interlocking are kind of opposing motion, and they're kind of restricting motion. And so the way you could successfully slide something across a table or a floor or whatever is you would have to push hard enough so you could break those bonds. So when you put two things that are supposedly nice and smooth, but they're not, and you put them on top of each other, the nooks and crannies kind of interlock like my fingers here are interlocking. And when you push them, they will prevent motion until you push hard enough so you can break those pieces free. And so after you've been moving something back and forth quite a bit, it's almost like you're sanding it down. Okay, so these are the two types of friction that we have. And we say static friction is non-sliding. So the reason why I'm able to walk across the floor is because when I put my foot on the ground, my foot stays on the ground and it doesn't slide off. So when I walk along the ground or when I drive my car along the road, I'm expecting static friction to give me a comfortable journey. Okay, so when I place my feet on the ground or when my tire rotates onto the pavement, I want no sliding at all to be involved, because if I'm driving my car and I'm sliding all over the place, or if I'm trying to walk across a parking lot and I'm sliding all over the place, then I'm not really in control, and no adult wants to do that. Okay, so and when we talk about kinetic friction, kinetic, it basically means motion. So when we have kinetic friction, there will be some sliding between the two surfaces. So if a kid gets on a sled and just slides down the hill, that's kinetic friction. If you're driving in your car very fast and you try to lock the brakes and you're skidding along the road, that's kinetic friction. Static friction is basically when there won't be any sliding between the two surfaces. The object can still move. If I'm walking across a parking lot, I'm moving, but when I put my foot on the ground, it stays exactly where I've placed it until I lift my foot off the ground. So my foot and the ground are in contact with each other, and they're not sliding. So when we say static, no sliding. Kinetic, sliding. And there's some formulas that govern how each of these work. So here's the formula for the first type of friction. So there's two types of friction. One of them is called the kinetic force of friction. Okay, so kinetic means there will be some motion between the two objects. There's going to be some sliding between the two surfaces. So we write it as this: force, subscript Fr, with a subscript small letter k for kinetic. And that is equal to, this is a Greek symbol. It looks like a U. It's actually called mu. And if you look in the textbook, it has a little bit of a line coming down the left side of it. So it's actually a Greek letter. And there's a subscript k there, also for the word kinetic. And then we multiply it by the normal force. So the normal force in this particular case would be coming from the drawing. So we talked earlier in Chapter 4 about how to do the free body diagram. So we'd have to calculate that. So in this particular case, the coefficient of kinetic friction is what this thing mu is. It's a coefficient. There's not going to be any units associated with it. And the closer we can get to 0, the less friction there is. So in Chapter 4, up until this point, we've been pretending there's been no friction. So you see, the coefficient of 0 would mean absolutely no friction. And the closer you can get to 1 means the two surfaces are rubbing against each other and it's rather rough. So if we can get all the way up to 1, there would be no sliding between those two surfaces. Okay, so it's a decimal point number, this thing called the coefficient. It's typically between 0 and 1. Most of your word problems will be between 0 and 1. There's no limit there. It could actually, it could go higher than 1. But for us, most of the time you will be between these two. Okay, so what we would do is typically we would look up in a table. So in our book, there's a table of coefficients of friction. You can find that in Chapter 4, Section 8, and they give you a lot of coefficient frictions for kinetic friction. Okay, so for instance, they might say, if this was a wooden box sliding on the wooden floor, they might just give you the fact that mu sub k equals 0.4. So they could just give that to you. Okay. Now, I could go up to this box and I could push on this box. So if I was over here and I was pushing on this box with an applied force of, let's just say, 60 newtons, and let's say the box has a certain mass to it. So the mass of this box could be, I could say, 15 kilograms. So what I would do is I would use my understanding of all the different forces, and I would go around and I would say, well, we have this thing called the weight, and the weight would be mass times gravity. So in this case, it would be 15 kilograms times 9.8, and that would come out to be 147 newtons. So that's the weight. The next thing I would say is I'm pushing on this thing only horizontally. I'm not pushing on it vertically at all. So what's going to happen is, in this particular case, the normal force would be equal and opposite to the weight. So the force normal would be 147 newtons also. And then the formula says you take the normal force, which we now have. We see the normal force, and we multiply it by mu, the coefficient of friction. So in this particular case, it would be 0.4, no units, times 147 newtons. And when I do that, I get 58.8. Okay. Now, that is my force of kinetic friction. So that means, if this was the case, and it has to be sliding for it to be called kinetic, so we are moving this box along the floor, but I'm pushing on it with an applied force of 60, but the force of friction is happening right here between where the two surfaces are sliding, so we have a force of friction going this way, and our force of friction, which is kinetic, is equal to 58.8 newtons. Okay, so one of the things we talked about in the beginning of Chapter 4 is draw a free body diagram and show every force acting on it. So I have the force of weight going down, I have the force normal going straight up, I have the force applied going to the right, and I have a force of friction going to the left. And we should simplify those if we can. So the force of weight is going down with 147, and the force normal is going up at 147. They will cancel each other out. There's a force going to the right of 60 and a force going to the left of 58.8. So I can simplify that picture and redraw my free body diagram and say that I will have one net force of, I would add these two together as vectors. So coming to the right is positive. So I take a positive 60 and I'll add it with this negative 58.8, and what I'll get is 1.2. So I'm pushing this box to the right with the force of 1.2. Excuse me, I'm not pushing it. This is now the net force. The net force is not a specific individual type of a force. I was pushing on it. The person was pushing on it with 60 newtons to the right. But the net force is 1.2 newtons. And the mass of this thing was 15 kilograms. So if you were asked what's the acceleration, of course, if this accelerates, it will accelerate going to the right. So we could say the acceleration equals the sum of all the forces over the mass. And in this case, it's going to be a positive 1.2 newtons divided by 15 kilograms. So the acceleration is going to come out to be very, very small, 0.08. 0.08, and the units there are meters per second squared. I think I ran them out a little bit. I'll write it again. The acceleration equals 0.08, and that's meters over second squared. So this force of friction, it comes out of nowhere, and it's going to try to oppose motion, and just because I'm pushing it to the right, it's going to be moving to the left. That's how to do this particular type of problem, dealing with kinetic forces of friction. So the second type of force that the frictional force, the second type of frictional force that the book talks about is this thing called the force of friction. Fr is friction, subscript static, static friction. Static friction occurs when there's no sliding between the two objects. So in this particular case, it's a little bit different because it says the force of static friction is going to be less than or equal to mu sub s times the normal force. Okay, so the force of static friction can be any number less than up to equal this. Now what is this? This right here is the braking force. If you pushed on something, for instance, as an example, here's a box, and there's friction between these two surfaces here. The box could be many different numbers. It could be anything. It could be a 10 kilogram box. It's just for an example. Let's say that I am pushing on it, and I push on it with an applied force of 5 newtons. So I push on it with my pinky, and I push on it with my pinky with 5 newtons of force. Well, everything has a breaking point. And if you went up to a kitchen table and you took your pinky and you tried to push the kitchen table with your pinky relatively lightly with a small force, most likely it wouldn't move. Okay? Because if this is not strong enough to break it free, let's just say for this example, the breaking force would come out to be, in this example, let me just make up a number, the breaking force is going to come out to be 25 newtons. Okay? So I have to actually get to 25 newtons, and breaking force actually means it's going to break free. Earlier in this lecture I said that friction could be considered on the microscopic level when two surfaces are trying to rub across each other. Friction could be considered like this, where they're interlocking, and we're trying to push the top one this way. So they're interlocking. So you see, if I push with a certain force, nothing happens. I push again, nothing happens. If I push hard enough, I might be able to physically break the tips of whatever's holding me back. I could break them off. If you had a table that was bolted to the ground, if you tried hard enough, I'm sure that you could figure out a way to kick the table legs in such a way to break the bolts off, to just break them free. And I'm sure if one person couldn't do that, then we could get a group of people together and simultaneously all try to kick and move that desk, and we could probably get it to break free. And that would physically be breaking the piece of the desk which is attached to the floor. It would be breaking it off, and now the table would slide. Well, we have to do that with static friction. There's these on the microscopic level. There's these micro pressure points which have almost been welded together, and we have to break them. So you see, if the breaking force, I'm throwing out the if the breaking force is 25 newtons, well, if I push with 5 newtons of force, that's not nearly enough to break it free, so it won't move. So in this case, my force of friction, static, is going to be 5 newtons. So I push with 5 newtons. It's not enough to break it free, so my force of friction static is 5 newtons. And if I decided to push a little bit harder, so it didn't move, so let me push a little bit harder. So if I draw the line a little bit longer, let's say I push with 10 newtons of force. Applied force is 10 newtons. It doesn't move because that's not enough to break it free. The force of friction static will be 10 newtons. Okay? So the force of friction static can be many, many different numbers until we get to some breaking force number. So I'm trying to move this box across the ground. I need to push at least with 25 newtons of friction force. That's as much as this static friction can withstand. Okay? Sometimes you might buy some rope, and it might say on the rope, or some fishing line, it might say on the fishing line that it's been tested and it can withstand up to 10 pounds of force. So somebody in a testing room has put that type of fishing line through a test, and they've pulled on it with machines, and they've been able to certify that it will not break, up till 10 pounds of force. Now, if you give it 11 pounds of force, you might be testing the limit. If you gave it 12 pounds of force, you might be testing the limit. 13 pounds of force may just snap that rope. And that's the same thing that would happen here. If we've been told that it's going to break at 25, well, in this case, it will break at exactly 25. So we have these pressure points, and we're trying to push something. So as we push, we're straining those pieces that are opposing motion. And the harder we push, the more they're straining. And when we push at a certain number, this one, the breaking point, it's going to move free. So if I just keep on increasing the number, so if I bring this number up to 20 newtons, it won't break free. That'll be 20 newtons. Okay. If I decide to bring this number up to 24.5 newtons, it won't break free. Okay. I could do this all day. I have to get up to 25. When I get up to 25, exactly at 25. So if I push this thing at 25 newtons, okay, then at that particular moment, the frictional force would be 25 newtons, but it won't maintain this because 25 newtons is the 25 newtons is the force needed to break it free. So if we apply 25 newtons to it, it will snap free, and if it snaps free, it's no longer static. If it snaps free, then it would be called kinetic. So you see, it won't maintain this 25 newtons of friction at all, because as soon as we get to it, it broke free. What does it mean if it breaks free? It means it's moving. Thus, static friction doesn't even exist anymore, because now it's a moving friction. So they have a graph for this type of a thing. And the way they graph it is usually this. So you could go and you could have an applied force and you could look at the frictional force. And as you go and you apply a small amount of force to it, then you'll have a small amount of frictional force, equal and opposite. If you applied more force, you'd have more frictional force. If you kept on applying more and more force, you keep on getting an equal and opposite frictional force until you get to the breaking point. So this is what happens here. And at the breaking point, it just snaps free, and then it ends up being down here a little bit, and it'll go along this way. So the force of friction going here, this would be static friction. And this would be kinetic friction. So you've probably experienced in life that you've tried to push something and you haven't been able to successfully push it because maybe it has too much friction. So you push it, it doesn't move. And you get yourself a little bit more prepared and you push it harder and it doesn't move. And you get yourself much more prepared and you push it for all you've got. You're pushing as hard as you can, and if it breaks free, what'll happen is the force of friction that it's experienced now will jump down quite a bit. So the kinetic force of friction is always going to be much less than the static force of friction. And so when it goes much, much less, then you're going to kind of like lunge forward. You're going to almost maybe fall forward because out of nowhere, you're going to get a much smaller opposing force because the force of kinetic friction is always smaller than the force of static friction. Okay. And the reason is it's just a factual thing. You could look it up in any table. Mu sub k is always going to be a smaller number than mu sub s. So the coefficient of kinetic friction is typically smaller than the coefficient of static friction. So if you looked up tables, they give you a lot of different circumstances. They talk about wood sliding on wood. They talk about a rubber tire sliding on concrete, wet concrete, or dry concrete. They talk about steel sliding on steel. And they give the cases when it's in static or when it's in kinetic. And the static number is always higher. Okay, so that just comes from experimentation. All right, let's try to do one of these problems. Here's a word problem where it says we have a 20 kilogram box which is at rest on a horizontal floor. Calculate the horizontal pushing force needed to start this box sliding across the floor. So I could draw it, and if I draw it, I would say here's my box, and it's 20 kilograms, and I want to push it, so I'm going to have some horizontal pushing force. And that will be an applied force, and that's what I'm looking for. How much force will get this thing to go? And I was told two things. I was told the mu sub s, the coefficient of static friction, is 0.5, no units. And the mu sub k, the coefficient of kinetic friction, is 0.3, no units. So, do the free body diagram. Draw every force that you can think of that's acting on this body. And the one I usually do first is the weight. So going from the center of the mass straight down, I would say weight. It's mass times gravity. So if I take mass of 20 times 9.8 for gravity, I will get that the weight is 196 newtons. Okay. The next one I'll do is the normal force. I'll look at the normal force. Since I'm only pushing horizontally, I'm not pushing on this box down at all or up. So if I'm only pushing horizontally, then the only thing that's going to cancel out this weight would be some vertical force, and this is the only thing it can be. The vertical force is normal, and it equals 196 newtons also. So I have that. Okay, and since it is at rest, that means it's not moving, that means it's not sliding. So I have a formula that I can use, and I have to know which one to use. I'm going to use the static one. I'm going to say the force of friction, static, equals mu sub s times the force normal. So mu sub s is 0.5. And the force normal is 196. So if I calculate that, that comes out to be 98 newtons. So this comes out to be 98 newtons. Okay. Well, what is that I'm doing? I'm actually not calculating. I'm not calculating the regular static frictional force. I'm calculating right here. I'm calculating the maximum. Because the maximum static frictional force is that moment when the object will break free and start to slide. So the maximum static frictional force would be this number, which means the amount of force that it can withstand is 98 newtons. So the force of friction, static, and we're talking about the max, is 98 newtons. So if I want this box to just begin to slide, if I push it with any other number lower than 98, it won't slide. If I push it with 50, it won't slide. If I push it with 90, it won't slide. If I push it with 97.5, it won't slide. If I push it with 98, it will break free and it will start to slide. So my answer would be 98 newtons. And then it will slide. Okay. I could ask a part B for this particular problem, and I could say, what would be the acceleration if I pushed on this with an applied force of 98 newtons? Okay. So as a part B, maybe I should just change the wording a little bit, because it's mostly going to be the same problem. Okay. So here's my part B, and it's a little bit tricky. So what it says is, if I push horizontally with 98 newtons of applied force on a 20 kilogram box, which is at rest, what's the acceleration of the box? Okay, and it's the same box as before, because it's just a part B. So we have the mu sub s is still 0.5, and the mu sub k is still 0.3. So here's what's happening. I didn't even redraw this picture here. So here's what happens. The applied force is going to be 98 newtons. The box was at rest. We were talking about static friction. The weight of it was here. The normal force was here. We calculated that the force of friction, static, the maximum, was going to be 98 newtons. So when the person pushes on the box with 98 newtons of force, as they do right now, think about it. What is going to be the acceleration of this box? And if I was in a classroom with you face to face, I would pause and ask you your opinion, because this is a tricky question. But I don't have that luxury, so you have to think about it. You can put the video on pause for a moment if you want. But here's what happens. This will no longer be here, because if I do push it with 98 newtons of force, then I will break it free, and if it breaks free, it's going to be moving, and if it's moving, it's no longer going to be static friction. So this number is based on static friction. So this number has to disappear. And you see, we had a formula for kinetic friction. And kinetic friction has this formula: the force of friction, small k, equals mu sub k times the force normal. And so we just plug this in. The force of kinetic friction is 0.3. no units, and we're multiplying it by 196 newtons. And when we plug that into our calculator, I need a calculator. Comes out to be 58.8. So now we have a force that's going this way, and it's a force of friction, and it's kinetic, of 58.8 newtons. Do you see how this is much different than it was a moment ago? A moment ago, the force of friction was 98 newtons. A moment ago, before I got to a pushing force of 98, if I was pushing at 90, the friction was equal and opposite at 90. When I pushed at 91, the friction force was 91. When I pushed at 95, the friction force was 95. When I pushed at 97.9, the friction force was 97.9. In all of those cases, there was no net force. All of them were canceling out. But now, when I get to 98, the pieces snap free, it becomes kinetic friction, and the kinetic friction coefficient is always smaller than the static one. So the kinetic force of friction is always going to be smaller than the static maximum one. And you see, now I have something that I didn't have a moment ago. These two forces are no longer equal and opposite. These two forces are unequal, and unequal forces are going to give me a net force. So out of nowhere, I'm going to have a net force, and the net force would be the difference between these two. So if I just take those two numbers and subtract them, I get almost a 40 Newton net force. I get 39.2. So if you added these up using vectors, 98 newtons going to the right, plus a negative 58.8 newtons going to the left, then what would happen is you would end up with 39.2 newtons. So I can try to draw it over here. I can say another free body diagram. Here is my 20 kilograms box. The force going up of 196 will cancel the force going down of 196. The force going to the right will cancel a little bit of the force going to the left. So I can get my net force by saying plus 98 newtons, and I'll add it with, because whenever I say sigma, it's the sum of, I'm adding, and I'll add it with a negative 58, and I'll add it with, so I'll say plus a negative 58.8 newtons. And when I do that, it will come out to be the sum of all these forces would be a positive 39.2. Okay. So if I know the net force is 39.2 and I know the mass is 20, then I can get the acceleration vector. The acceleration vector would equal the sum of all the forces over m. So it's going to be 39.2 newtons divided by 20 kilograms. And the acceleration vector would end up equaling 1.96 meters per second squared. Okay. So that's how to answer this problem, and it is a little bit of a tricky problem, and the tricky piece came from the fact that for part A, I had calculated what is the maximum pushing force to just get it moving. So for part B, I said, how about if we push it that force to just get it moving? What's the acceleration? And many students wouldn't notice that we have now a different type of friction involved.